Hi. Today in this video, you will learn how to solve exact or non-exact ODE. The general form of these type of differential equations is using method explained. In this video, you will be able to get solution of the given differential equation in this form. To approach the solution, follow 3 simple steps. Number 1, check for exactness. Number 2, if the given ODE is not exact, then make it exact by multiplying it with a function called integrating factor. And number 3, solve the exact ODE to get the final solution. Let us explain this method to you with the help of a problem from textbook. In this problem we have to check the given ordinary differential equation for exactness, and if it's not exact, then we have to make it exact to get our final solution. First step, let coefficients of the terms dx and dy equal to m and n. Second step, check for exactness. For given ODE to be exact, following condition must be satisfied, that is, partial derivative of n with respect to y must be equal to partial derivative of n with respect to x. After putting values of m and n and doing necessary calculation, we get that our given ODE is not exact. So to approach the solution, we first have to make the given ODE exact. If a differential equation m dx and d equals 0 is not exact, then we can make it exact by multiplying the given ODE with a function called integrating factor f such that we use following 2 formulas for find integrating factor r. Which formula we have to use depends on 2 conditions. First condition is, if value of 1 over n into partial derivative of n with respect to y minus partial derivative of n with respect to x is a function of x only, then formula for finding integrating factor will be second condition is, if value of 1 over m into partial derivative of n with respect to x minus partial derivative of n with respect to y is a function of y only, then formula for finding integrating factor will be. Let's get back to our problem. In our problem we found that first condition is true, so our integrating factor will be in next step, we multiply the given ODE with integrating factor we calculated in previous step. After making the necessary calculations, we get exact, ordinary differential equation. We can also check that the new differential equation obtained is exact by repeating the step 1 and 2 for this equation. In next step we move towards solving the exact equation. First, integrate m with respect to x. Note that in this step we add a constant of integration k of y, the value of which will be found later. Now we have to calculate value of k, the integrating factor, by taking partial derivative of u with respect to y, of the equation 1 in previous step. Follow steps, as shown, to get the value of k. This is the final step of our method. Here, we put the value of integrating factor, obtained from previous step in equation 1. As it is explained in the beginning step that our solution is of the form u of x, y equals